Final podcast. This one is on intermolecular forces, which we also call IMFs. Okay. So first, let's get clear about terminology. So we have intramolecular forces and we have intermolecular forces. Intramolecular forces are the forces within the molecule. So if I have a water molecule, the intramolecular force is the covalent bond that attaches the hydrogen to the oxygen, as opposed to an intermolecular force where the water is attracted to adjacent waters. There is an attraction here, attraction here. This is the intermolecular force, and that is the focus of this podcast, the intermolecular forces. So let's define some things first. So intermolecular force is the force of attraction between molecules. Okay. Boiling point is a good indication of how strong those attractions are. High boiling point means high attraction. Low boiling point means low attraction, and we'll talk about why that is in a minute. And intermolecular forces are generally weaker than the forces between atoms that make up the molecule. And what that means is forces between the molecule means the covalent bond that creates one water molecule, that creates the connection between oxygen and hydrogen. That bond has a stronger attraction than the connection or the attraction between two adjacent waters, right? So the covalent bonds are stronger than IMFs. Alright, so there are three types of IMF, and the first is called dispersion forces, and it is the weakest. Okay, so dispersion forces are sometimes, you'll hear people call them London dispersion forces or van der Waals forces. And these are intermolecular attractions resulting from the movement, these notes are in your packet, movement of electrons in the creation of temporary or instantaneous dipoles. And dispersion forces are present in all molecules, whether they are polar or nonpolar. And they are stronger with atoms or molecules of greater mass, and that is because they have more electrons. So let's take a look at London dispersion forces. Okay. Alright, so here we have a nonpolar substance, let's say a nonpolar molecular substance. And we have the molecules next to each other, and even though they're nonpolar, it's possible for a split second that there are more electrons on one side of the molecule than there are on the other. Okay? It's a quick temporary thing. So while they're actually the probability is spread out, for any given second they can be shifted so that one side's more negative and one's more positive. Okay, and when that happens, part of the molecule becomes more negative than the other side, which becomes more positive. But what happens as a result of that is this molecule that now has a temporary dipole can induce a dipole on an adjacent molecule. So this side becomes more positive, this side becomes more negative. So let's take a look at that effect on the neighbors. Okay, so as that happens, you have adjacent molecules also line up with dispersion forces, and we call these London forces. Okay. So they are temporary. You can see they come and they go. They are relatively fleeting. Okay. The second type of force, here's another example of dipole forces. Here we have argon molecules. As you know, argon is a noble gas. It's got a full outer shell, and it's possible, just like in the molecule, that the electron concentration is greater on one side temporarily than on the other, right? and that will induce, this side would be more positive, it'll induce a dipole on this adjacent one, making this side more negative, this side more positive. And what you end up with this is a dipole. More electrons here, fewer here, more electrons here, fewer here, causing this attraction between molecules, even between something as simple as argon, which is a noble gas. So let's take a look at a graph that shows what happens to boiling point as we increase. Okay, so here we have noble gases: helium, neon, argon, and krypton. And what you see is as the molar mass increases, the number of or the temperature at which it boils increases. And as you know, boiling occurs when a molecule can escape, or an atom can escape the surface of a liquid, gets enough energy to do that. Well, krypton has a higher boiling point because it requires more energy because there's more electrons, which means the dipole, the dispersion forces, can be greater in krypton than they can when there's fewer electrons in the other example. So let's just take a quick peek at that. So if I have a bunch of kryptons, boiling means that this one has to escape, has to get enough energy to break attractions between molecules. Well, if this is krypton, because krypton has more electrons than, let's say, helium, it can have stronger dispersion forces. So this side becomes more negative, then these interactions become stronger than they would, let's say, with a smaller helium where I have fewer electrons. So the higher the molar mass, that means the higher number of electrons, which means the higher boiling point. Okay. And here you can see, here's the noble gases that we plotted, right? Xenon would have the highest dispersion forces and therefore the higher molar mass. But in the case of the halogens here, this is group 17, we see the same increase, but at this time it's to the point where it actually makes a difference in the state of matter at room temperature. So as you know, fluorine and chlorine are gases at room temperature. They have very low dispersion forces. Doesn't take much energy to separate the attractions between them. But as you increase the mass and therefore the number of electrons in bromine, now you have it's more difficult to break these attractions because I can have greater dispersion forces. So now bromine is actually a liquid at room temperature. It takes more energy, so I need temperatures above room temperature for one of the bromines to escape. And when I get down to iodine, iodine is even more massive and has more electrons. And iodine actually exists as a solid, a crystalline solid, a very pretty purple solid at room temperature, because the attractions between it are much greater than they are with even bromine, because now we have a whole lot more electrons. So even though iodide itself is nonpolar, the fact that we can have these temporary dipoles and there's lots of electrons makes for some attraction. So dipole forces. So all, only, trying to use this pen. Alright, sorry. Only polar molecules have dipole forces. And a dipole is opposite charges separated by a short distance. So for instance, I have hydrochloric acid, and then I have another hydrochloric acid. This side's relatively positive, this side's relatively negative. Same thing on the adjacent one, causing attraction between the two hydrochloric acids. It's called a dipole-dipole. Let's take a look at what this looks like. So let's say this is the HCl, the blue part is the hydrogen, the green part is the chlorine. We can see the dipole within the molecule. There's a positive pole here, negative pole here. This is a dipole. Adjacent molecules have a dipole. And what happens with dipole forces is they line up. And that's the dipole-dipole interaction. So this is what it would look like in a solid or even in a liquid, is they would all line up, kind of like little soldiers here in a nice, neat line, with the more positive side attracted to the more negative side of adjacent molecules and form this whole network. Okay. The third and last type of hydrogen